Good boy. You're okay. Oof. Oof. Woof woof. Is it little doggo? Little doggo? Little doggo? Can I get a num num? Can I get a num num? Num num. Num num. Bugger. Num num. Num num. Num num bugger. Rejected. Hello, class. Gonna wait for a couple more people to join the live stream, then I'll get started. Please let me know. That one's bug. Please let me know if the live stream stops working. I've been having some internet issues this past week, so my first period class was a major fail this morning. I don't know why, but my internet was not working. So I think I got it fixed now. But yeah. All right, I think I'm going to go ahead and get started, even though only 10 people are watching. So we're going to continue talking about simple harmonic motion today. So just to remind you, the equation of simple harmonic motion is minus omega squared times the quantity x minus c equals the acceleration. And anytime you have an equation of this form, you know that the position as a function of time is going to be given by c plus a cosine of omega t plus phi. Okay. Now, what do each of these constants mean? C is the particle that's moving is oscillating about x equals c. Okay. A and phi are what are called initial conditions. And so the initial conditions have to do with when do you start the system oscillating and how much energy do you give it. And then omega is related to the period, and through the equation, period is 2 pi over omega, and it is determined by the properties of the system. Okay. So today we're going to focus on the mass spring system. And in particular, we're going to talk about energy. Energy in the mass spring system. So just to remind you what the mass spring system is, we have a spring. The spring has a stiffness K, and it's attached to a mass m, okay, and it's stretched. So we're actually going to call this location right here, we'll call that x equals 0, okay? And so this spring, or the mass, is pulled so that it's at x equals a. All right? And what's going to happen is it's going to oscillate back and forth as time goes on. Okay, so what will happen is after you release the mass, the elastic force is going to pull it towards x equals 0. So it's going to start moving towards x equals 0. All right? And as it moves towards x equals 0, it's going to pick up speed. Okay? And actually, when it reaches x equals 0, it has the most speed. Okay? And the reason for that is that the mass spring system is losing elastic potential energy and gaining kinetic energy. Once it passes by x equals 0, it then starts compressing the spring, so it starts losing kinetic energy and regaining its elastic potential energy. So we have, when it's right here, it's going to start to slow down. And then once it gets to the other side, which would be at x equals negative a, it is at rest again. And then the spring pushes it back in the other direction. It goes back and forth. So we could think about the mass spring system, okay, or actually simple harmonic motion in general is an exchange of energy between potential energy to kinetic, back to potential, back to kinetic, back to potential, back and forth over and over again, okay? So if we think about right here, the mass is at its extreme point, so it's not moving. If it was moving, it would be going further to the right. But because it's not moving, the energy is not made up out of kinetic energy at all. It's all elastic potential. So right here at this point in time, the energy is going to be all elastic potential energy. So 1/2 Ka squared. Recall the formula for elastic potential energy is 1/2 Kx squared. But at this particular value of x, this value of x is capital A. Right here, the mass is moving and the spring is stretched. So right here at this point, we have both elastic potential energy, okay, and kinetic energy. All right. So that's at that particular instant. Right here, we're at x equals 0. If you're at x equals 0, because the formula for elastic potential energy is 1/2 Kx squared, if you're at x equals 0, you have no elastic potential energy. So all of the energy is kinetic energy. And because all of the energy is kinetic, the speed is going to be its maximum value, 1/2 m v max squared. Okay, so all three of these expressions for the energy are the same because the energy is conserved, but the breakdown of the energy in terms of kinetic and potential is changing as it moves back and forth. Okay. So I would like to go ahead and prove to you that energy is conserved, okay, in a mass spring system. So first of all, let's just go back to the basic equation for the mass spring system. So we have The net force is the elastic force minus kx, and that equals ma. All right. Divide both sides by m. All right. And then we compare that to the equation minus omega squared x minus c equals a. So we can see that this comparison works if we have omega squared equals k over m, and we have c equals 0. Okay? So of course that means that omega is square root of k over m, and that means that the period is 2 pi square root of m over k. All right, so this is an important equation. It's the period of the mass spring system. All right. So we know that the position as a function of time is going to be a cosine of omega t plus phi. There's no constant term because the constant is 0. I can take the derivative of this expression, and I can get that the velocity as a function of time is minus a omega sine of omega t plus phi. And I could even take the derivative again and get that the acceleration as a function of time is minus a omega squared cosine of omega t plus phi. All right. Now, so this just came from taking the derivative of the previous. Now, this actually gives us a lot of useful information. And the reason is this. The sine function and the cosine function both wiggle between +1 and -1. So a omega times sine is going to wiggle between plus a omega and minus a omega. So what that means is we can actually use this to get the maximum speed. So the maximum speed is going to be a omega. Right? Because sine is wiggling between +1 and -1. So a omega times sine is going to wiggle between a omega and minus a omega. Similarly, by a similar argument, we can show that the maximum acceleration is a omega squared. Keep in mind that capital A stands for amplitude and lowercase a stands for acceleration. All right, so that's nice. So now I would like to prove that the energy is conserved for simple harmonic motion of the mass spring system. So how are we going to do that? Well, energy is kinetic plus potential. The kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. So now what I'm going to do is I'm going to plug this in for x, and I'm going to plug this in for velocity. All right? So what happens when I square this? Well, squaring -1 gives me +1. And then I just square each of these terms individually. So I have a squared omega squared sine squared of stuff. I'm not going to write the argument because it's going to be the same for everything. Plus 1/2 k times the position squared. Well, now I have to square this one, so I get a squared cosine squared of stuff. All right. Now, if we look at this equation up here, omega squared is k over m, so that means that m omega squared is k, just by multiplying both sides by m. And so what that means, see how I have m omega squared here? So I get 1/2 k, so these two combine to make k. 1/2 k a squared sine squared plus 1/2 k a squared cosine squared. So you can see that I have a sine squared plus a cosine squared, which is just 1. So I get that the total energy is 1/2 ka squared. All right, which is a constant. It doesn't have anything that depends on time. So we've just proved that the energy of the mass spring system is conserved. And as I wrote up here, I'll just write it again just for clarity. All three of these expressions give the same energy. All right, so we could also write it as 1/2 m v max squared, or we could write it as 1/2 mv squared plus 1/2 kx squared. All right, so that's nice. I'm going to go ahead and derive another useful equation. So it comes from this equation. So the energy is 1/2 ka squared, but I can also express it as 1/2 mv squared plus 1/2 kx squared. All right. So the first thing I'm going to do is I'm going to cancel out the 1/2s because everything has 1/2. So I have ka squared equals mv squared plus kx squared. Then I'm going to subtract this kx squared to the other side. All right. Then I'm going to divide both sides by m. And then I'm going to take the square root. So this gives me the speed as a function of position. So that's kind of a useful equation, so I thought I would derive it for you. Okay? All right, so we're going to do an example. And then we're pretty much done. So we have a 3 kilogram mass is attached to a spring of stiffness (100 newtons per meter). The mass is pulled back (0.4 meters) and released from rest. At position 0 and time 0, the mass has a collision it's completely inelastic with a 2 kilogram mass. Okay, and so what we want to write, we want to write what is the position as a function of time. Okay, so the position as a function of time is of course going to be x of t equals a cosine of omega t plus phi. So let me draw a quick picture of what this looks like, just to make sure that you guys understand. You've got, here's x equals 0. All right. You've got a mass that is pulled to the right a distance. So this distance right here would be 0.4 meters. Okay. And here's the spring, it's stretched. And then the mass is released, so it goes that way. And when it gets to the middle, it has a completely inelastic collision with a 2 kilogram mass. All right. And so completely inelastic collision means they collide and they stick together. So afterwards, this pair is going to be compressed. They're going to be compressing the spring, and they'll go back and forth. Okay. But one of the important things here is because during this collision, the 3 kilogram mass is going to slow down. Some of that energy is going to be dissipated as heat. And so the amplitude is not going to be 0.4 meters after the collision. Okay? So what we have to do is we have to figure out what is the amplitude. All right? And by the way, when this collision happens, that is defined as time 0. Okay? So in between here and the collision, energy is conserved. It's only during the collision that energy is dissipated as heat. So the energy at release is equal to the energy just before the collision. All right? At release, the energy is entirely elastic potential. Just before collision, the energy is entirely kinetic energy because the collision happens at x equals 0. Okay, so I'm going to plug in numbers here. So canceling out the 1/2, I get 100 times 0.4. 0.4 would be the amplitude in the absence of the collision. So this is at release. It's pulled 0.4 meters to the right. It's 3 V max squared. And so that's going to allow me to get the maximum speed. So the maximum speed, so that's the speed just before collision, is 2.3 meters per second. All right? Now, during the collision, I'm going to use conservation of momentum. So this is a completely inelastic collision. So I have P initial equals P final because momentum is conserved. So initially, we have 3 kilograms moving to the left at 2.3 meters per second. Okay. Afterwards, we have 5 kilograms because it's 2 kilograms and 3 kilograms moving together at an undetermined final velocity. So we can solve that for V final after the collision. And we get after the collision, the speed is 1.39 meters per second. So, so we can see that some of that energy was dissipated. It slowed down. Okay. Now, after the collision has happened, we have no more energy dissipated. So now we can use conservation of energy once again. All right. And so the pair is going to continue and compress the spring. And so the energy just after collision is going to be equal to the energy at full compression. So just after collision, because the collision happened at x equals 0, we have only kinetic energy. And at full compression, the pair of masses is not moving anymore. So we have all elastic potential at full compression. All right. So again, I'll cancel out the 1/2. And the mass after the collision, I have 5 kilograms moving, not 3 kilograms like we did here. We know that the speed just after the collision is 1.39. And the K value is 100. So I can get the amplitude. This says that the amplitude is 0.31 meters is the amplitude. Okay. So I know that this number right here is 0.31. All right. Omega, from the previous page, omega is square root of k over n. So I have square root of 100 divided by 5. That's square root of 20, which is 4.5 radians per second. So here we have 4.5. So now the question is, what is phi? All right, and if we think about it, time 0, the blocks are at position 0. They're at x equals 0 at time 0. Okay. So that means that it has to be a sine function, because sine, not cosine, is the one that starts out at 0. Okay. Furthermore, the masses are headed to the left at time 0, so that means they have a negative velocity. So the trig function that starts out at 0 and has a negative velocity initially is negative sine. So negative sine looks like this. You get what I'm saying? So that means that the position as a function of time is equal to negative 0.31 sine of 4.5 t. So that's the position as a function of time. All right. So I have one more little thing, and then we'll switch over to the zoom in. What if you have a vertical mass spring system? Okay, a vertical mass spring system you have the spring is hanging vertically, and then the mass is here. Okay, so now gravity is going to play a role. So if we were to do Newton's second law for the vertical mass spring system, we don't just have the elastic force, we have the elastic force and gravity. So we have minus kx, and we also have minus mg. So what I'm going to do is I'm going to go ahead and factor out a negative k on the left-hand side. So that gives x plus mg over k. That's a. And then I'm going to divide both sides by m. All right. So now what we'll do is we'll compare that to the fundamental equation of simple harmonic motion. So who can tell me what is the c value and what is the omega squared value? Oh wait, type it in the chat if you know. Dum-de-dum. Very good, yeah. So by comparison here, we can see that c is negative mg over k. And omega squared is just k over m. So the first point is that omega squared is the same as it was when it was vibrating horizontally. So you might think that having the mass spring system vertically, now gravity is going to somehow change the period of oscillation, but it doesn't. Okay, if you take a mass spring system and you move it to another planet, it's still going to oscillate with the same period. The period only depends on the stiffness of the spring and the mass that's connected to the end of it. Okay, so that's kind of maybe counterintuitive to some people. But what does change is instead of the system oscillating about c equals 0, it oscillates about a negative value of c. So what that means is that gravity is going to stretch the spring so that it's oscillating about a sagged position. The spring is going to be stretched and it's going to sag and it's going to oscillate about that position instead. And the more gravity there is, it's not going to change the period of oscillation, but it's going to change how much the mass is sagging below its original position. Okay? So that is my lesson. Excuse me. That is my lesson for today. And I will see you in the Zoom room for further discussion.